All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 318, Electronic Circuit 1. Today is our 23rd lecture. Okay. And here we are watching the Gantt chart, and we are at this very cell right here, right before the Thanksgiving break. Okay. This cell here, Tuesday. And also the first lecture for the very last module 6, the basic BJT amplifiers. Okay. According to the pattern from MOSFET, we should know is bunch of circuit analysis, AC analysis. Okay. And to do AC analysis, we need to be aware that DC analysis goes first, right? DC analysis goes first. What's the reason for DC analysis goes first? Anyone still remember? By the way, can you guys hear me? Good. Okay. The noise is right. Okay. We need ID. We need ID back in the MOSFET. Okay. We need ID. I need ID for calculating the AC small signal parameter in MOSFET. And here in BJT AC analysis, the pattern remains same. Okay. The pattern remains same. We need something out of the DC analysis to calculate the AC small signal parameter too. Okay, so it's pretty much the same pattern. Okay, so it should be much easier than MOSFET. And today lecture, we will spend majority of time actually on reviewing the midterm 2, which we haven't done yet. Okay, and especially concerning the close relationship, or say close pattern between two transistors. Okay, we want to spend enough time on reviewing the details of midterm 2. Okay, because from this small signal circuit, I'm seeing still quite a bit trouble. Okay, quite a bit trouble. All right, let's first of all start our module 6. Module 6 and a little bit, and then leave the rest of the time for reviewing the midterm 2. Okay. First, this is I think probably the very last time for this semester to review this table content. Okay. So what we are seeing is actually we have done chapter 1, 2, 3, 4, and 5. So only chapter 6 here left. Okay. Only here left. Yeah, the very last module. Following the same pattern. And chapter 6. But first of all, some basic concepts here. So to work as linear amplifier, because there are two applications the transistor can work as, right? One is just a switch, on or off, two states. Another application for transistor is the amplifier. Okay? We call it linear amplifier. Okay, and we are expecting to see the output, AC output. Could be very careful. Yeah, AC output. Okay. Once again, we are talking about linear amplifier, this particular application for transistor. We're expecting to see the output AC is proportional to input AC. So here, this gain relation between input and output refer to AC and AC only. Okay, be very careful. The gain is AC gain, not DC gain, not AC plus DC gain either. Is that clear?
Yep.
Good. Thank you, Shane. Shane is very responsive, and I appreciate that. And by the way, what DC analysis for? DC circuit and analysis is just for what? Locating your Q point, quiescent point. Okay, locating the Q point inside of the, what is it? Active region. Okay, remember. if your Q point from the DC analysis is not locating your Q point into the active region, first of all, the BJT is not functioning as amplifier at all. Okay, so the DC circuit is guaranteeing the location of the Q point is in the active region. Okay, now this is what DC for. Same thing in the MOSFET. And of course, if you're talking about output signal, and output signal is, yes, is sum of DC and AC. In other words, you have offset DC, and then on the top of that, you have AC signal swinging. This is very simple because you have both AC input and the DC supply up there, right? So your output signal is definitely the result of both based on the superposition principle. This concept needs to be clear. Okay. Output signal is output signal. The gain is AC gain. Okay. These are two different things, two different concepts. Okay. Right. DC response from DC analysis, AC response from AC analysis. Okay. The summation of two is the total output signal. And this AC amplification behavior could be described as this IV curve with load line. Okay. IV curve is plotted in pink color, dashed line. Okay. So we have more than one IV curve here. Okay. They're corresponding to different what? Anyone still remember? Different what? Anyone remember? Every time we show the IV curve, we always see more than one IV curve. Okay. Same thing in the MOSFET IV curve. However, what is the difference then among them? What's the difference?
Was it IB?
Correct. Okay. Noah is right. Okay. Different IB. Okay. Different IB. Okay. This IB1. You have one curve, you have IB2, you have second curve, and so on, so forth. And it, of course, makes perfect sense that with increase of the IB, your IB curve is kind of shifting upward, right? That makes perfect sense. Okay. So different IB level giving you different IB curve. Okay. And load line is the solid black color line intersecting with bunch of IB curve. How to understand this? This is actually, okay, load line is established by DC circuit. DC circuit give you a load line. Once you have this solid black line, it intersecting with the IB curve. IB curve, which IB curve it is operating at, is up to the IB. IB is due to the input AC input voltage. And that AC gonna make the IB curve changing. Since AC is going up and then going down and back and forth, then your swing of your output IC and VCE is also swinging. This is the projection of the VC due to the swing of IB. Why IB is swinging once again is due to the AC input. Okay, this is how we interpret this curve. Okay, how we interpret this curve. AC input, okay, IB, then gonna be AC swing. Positive, negative swing. This is the characteristic of the AC, right? IB swing, okay, then so your intersection point between the load line and the IB curve gonna swing as well, right? And then introducing swinging IC and VCE. It makes perfect sense. IC, VCE, they are the output current and voltage. They're AC. Perfect sense. IB swing introducing AC output. IC, VC, they're saving too. Perfect sense. Okay. So if we increase the IB, then how IC and VCE gonna change? We have discussed this already, actually, right? We increase our IB, the intersection point between the load line and IB curve is moving what? It's moving towards left, or say upper left, right? Upper left, towards this way. Introducing the VCE gonna decrease, and IC gonna increase. This is a little bit explanation for the AC amplifier operation. But once again, the same pattern, same idea as we learned from the MOSFET. Okay. And here in MOSFET, we also begin with the AC equivalent circuit before introducing the small signal model for the MOSFET, right? So we are doing the same thing here. Given a circuit here, you're seeing a DC power supply on top, taking care of the DC circuit Q point, and also, of course, AC input. We're expecting to see output AC, see the amplified AC from the output. Here, there's a DC biasing, for whatever reason. And how to find AC equivalent circuit? We are shorting the DC voltage source. VBB shorted to the ground. VCC shorted to ground as well. Right? VCC shorted to ground as well. So if you flip RC down, and so that you can short the ground up here and the ground down here, and then ended up with this AC equivalent circuit. AC equivalent circuit. This is not something difficult. However, be careful. This is not small signal circuit yet. Okay, this is not small signal circuit yet. Okay, we call it AC equivalent circuit, which means we have eliminated all of the DC, right, and shorted all of the capacitors. However, we are not using the BDT transistor small signal model yet. Okay. We are not using the small signal model yet. That's what does mean. That's what does this AC equivalent circuit mean. Okay. This is just taking care of the DC and the capacitor. Okay. Not small signal circuit yet. And to introduce the small signal circuit, we need to talk about the parameters first. Okay, we have some parameters. So first of all, your IC in AC small signal circuit equals to GM times VBE. Okay, VBE. GM is transconductance. We learned this term actually back in MOSFET as well. Right? This is not a new term. GM is not a new term. Okay. Transconductance. How we calculate the GM? GM equals to ICQ divided by VT. So ICQ is what? What is ICQ? Anyone knows? What is ICQ?
That IC from the DC analysis.
Good. Sounds like two and Noah know the answer. So this is a DC result. ICQ is nothing but DC result. Apologize for my writing. This is the best I can do with my mouse. Okay. DC result. Also explained once again why we need to conduct the DC analysis first. Right. And the denominator here is the VT. What is VT? Anyone remember this?
That's the thermal voltage.
Good. Again, more than one student real know the answer. Good. Thermal voltage. And what's the value then? It's about 26 millivolts. Right? Be very careful. It's millivolts. Okay, so it's not volts. In microelectronic circuit, we won't have 26 volts. That's ridiculous. Okay, millivolts. One that's constant thermal voltage. Very good. Okay, this is how we calculate the GM. We definitely need it. Definitely. Second, VBE is what? VBE is the voltage between base and the emitter in AC circuit, in AC small signal circuit, and this voltage equals to IB times R pi. Okay. We don't know who is R pi yet, but we will see the circuit. Okay. IB is obviously the base current. So the base current times R pi equals to the VBE. Okay. This is nothing but Ohm's law. Okay, you can easily guess. So the IB base current is also going through this R pi, we will see. Okay. And also the output resistance. This is another thing we need to calculate at the beginning of the small signal circuit analysis, right? What do you see? Same pattern, right? Isn't it? VA over ICQ. ICQ is DC result. We know it. VA is what? Anyone remember? Who is VA? Early voltage. Very good. Okay. Early voltage. Very good. Okay. And then, generally speaking, this early voltage is what? What word we should use to describe it? Infinity. Well, infinity. It is the easiest case, right? Generally speaking, we can call it as big. Okay, VA is big. Yeah, VA is big. Not necessarily infinity. Okay. If it is infinity, obviously the R naught is the infinity too. Therefore, it's open circuit. We call it the easiest case, right? But is it infinity or a big constant? It's up to the given, up to the problem. Okay. Of course. By the way, VA equals to 1 over lambda. Lambda is called the channel length modulation parameter. Okay. Generally speaking, we're going to give VA directly. Okay. But textbook problem homework might use lambda. One more step. Early voltage definition remains same. You're reversely extending the IB curve, and then they're going to merge to one point along the x-axis. Okay. The voltage is equals to negative VA, and that voltage is negative VA. Okay. So far, you can easily feel that actually everything is following the similar pattern from MOSFET. And here, obviously, page 7. And it's page 7 in this lecture. You need to print out as your handout. Okay. It's, by side during the exam. You need this handout. You need this page as handout. Okay. Here, because we have two types of BJT, NPN and PNP. Right? As here is once again, just showing your NPN, and you will see. Or say emphasize the difference between the PNP and NPN, right? And here are repeating the parameters you need to calculate at the first place, right? With experience from the MOSFET, these are very easy, very straightforward. You know what to do. You know what to do. Okay. What to do. Oh, of course, here, this is something new. This is something new. R pi. R pi. R pi is something new. Look at where is R pi in the small signal model. This R pi. No wonder it's new equation, right? No wonder why this is a new equation. Because in MOSFET, what we had at here? Nothing, right? In MOSFET, this is an open circuit. Of course, we don't have any R pi. And there is significant difference between the MOSFET and the BJT is the gate of the MOSFET is open circuit. Okay, there's no current. However, there is current in the base for BJT. Okay, so here is not open circuit anymore. Instead, we have a resistance R pi, whose value is calculated by this new equation here. Okay. Not 2 parameters, but 3 for BJT. Okay. So, and across this R pi, we have a voltage V pi. Who is V pi? Can anyone tell who is V pi actually? You're not confused. V pi is nothing but VBE. Okay. Feel free to use VBE actually in the exam or homework anywhere. We don't have to use V pi. VBE is actually, in my opinion, more meaningful, right? Just like VGS in the MOSFET. Here is VBE, the voltage between 2 terminals, base and emitter. Perfect sense. And dependent current source for NPN is downwards, and current value equals to GM times VBE. So it's just as simple as this, right? As simple as this. You have a R pi, a voltage process is VBE, and you have a dependent current source whose value equals to GM times V pi. Once again, NPN, okay, this is NPN BJT. NPN BJT. Let's do an interesting thing, okay? I'm not teaching you the PNP, right? However, based on the experience from the MOSFET, what does the small signal model for PNP look like? Give you guys 30 minutes to draw this on your notes. Go ahead, 30 seconds. And I will present the PNP small signal model under the dog cap. Well, of course, if you read carefully, the answer is already presented in the slide, but I still want you to try this. Based on the experience from the MOSFET, what's the difference between PNP and NPN? Repeating. All right, let's see. So I'm repeating the NPN, right? This is NPN. PNP, I'm using the red, right? PNP, I'm using the red. So what's the difference? It's definitely opposite polarity right here. Not VB, but VEB, right? Not VBE, but VEB. Current source flipped, correct. Correct. Flipped, and also the value is GM times VEB. Right? That's it. Yep, Shane is right. Right. Just these two differences. By plotting them together with different color, I'm emphasizing the difference. Okay, it's more visible. Small signal model for NPN and PNP. You need this this page as handout, apparently, including also 3 equations for the parameters. Right? So any questions? Since this is the obviously this is the most important page today for today.
Does the direction for IB and IC change as well with the BNP?
A very good question. Very, very good question. Well, the thing is, we seems not emphasizing them. However, they are changing. They are absolutely changing. Okay, very good question. Hold on. Let me do this. If you're talking about here, IB, right? Here, IC, right? Be careful, I'm using blue. Blue means the NPN, okay? IB here, IC here. IE is downward, right? IE is downward. Okay. I'm using red to label the current direction for the PNP. PNP, what happened? Same in the DC, same in the DC. IE is going into it. Okay. IE is going into it, flowing into the emitter transistor, say. And the current here is like this. IC is here, this IE. IB is also reversed, direction reversed. Okay. And recalling in the DC analysis for the BDT, what happened, and NPN, PNP, the current direction flipped, opposite. In AC as well, AC as well. They're having opposite current direction. However, no matter it's blue or red, what do you see? They have same current relationship, right? They both are have what? In AC as well, right? IE equals to IB plus IC. No problem. NPN, PNP, same current relationship. This is, of course, AC relationship, which is same as the DC current relationship. Okay? And from here, it actually makes more sense. If you do a KCL at emitter, this node, you can come up with this conclusion, right? Good. Good. Any other questions? All right, we can move on. So this is talking about how to come up with the small signal circuit, okay, the entire circuit, not only the BJT transistor itself, but also the entire circuit, like the biasing RC, RB, and the input AC source, right? So how to do that? Same thing. We have done quite a bit for MOSFET circuit, right? We're extending the circuit terminal by terminal. Okay? Always follow such kind of procedure. You're placing, first of all, the small signal model of the transistor right in the middle of the paper, right? And then extending the circuit terminal by terminal, following such order. Okay? going to minimize the possibility of missing any element of the circuit. So I don't think I need to teach anything, but give you guys 1 minute to find out the small signal circuit for this given circuit here. 1 minute. Go ahead. Small signal circuit for it. Go ahead. All right, let's see the solution here. So this is the small signal circuit. It should be fairly easy. Right in the middle, the dashed line box is containing the small signal model. The small signal model. Of course, here we are not involving, well, so far we are not involving the output resistance then. But if we do, where is the output resistor? This is actually same as MOSFET. It's always what? Between collector and emitter. And this is where the output resistance is. Regardless the ground, okay, regardless where is the ground, okay. I saw this mistake happen more than a couple of times in the exam, actually. R0 is between the drain and what? The source, right, for MOSFET. And here is between collector and the emitter. Has nothing to do with ground, okay? Emitter might be, by some chance, to be the ground as well. However, still the nature is between the collector and the emitter. Okay, you forget about the ground. Okay, forget about the ground. So if we involve this R0 here, then this is the result. R0 parallel with RC here. Okay, RB here connect to the base. And then the other end connect to the positive polarity of the AC input source. Okay. Emitter here is nothing but ground, very straightforward. Collector is output. Okay, collector is output. And also connect to RC. The other end of RC is ground. So this is the small signal circuit. Any questions? Any? You can expect in future analysis, well, the difference is basically here, right? The analysis-wise, the equation-wise is going to be different from the MOSFET because of this R pi. Because of the presence of the R pi. Okay. But the principle remains same. KVL, KCL. And here, let's just briefly go through this given analysis procedure, which obviously is another handout you should have. DC analysis always goes first, okay? DC analysis always goes first. And to AC analysis, you need to, first of all, calculate 3 parameters at the beginning. And the equation formula is available at page 7, right? Page 7. This lecture 20 means the PPT slides 20 rather than lecture 20, because lecture is obviously 23. Anyways, this is one handout. Okay, the most important page for today. Okay, page 7. And then second, you go ahead to find the circuit. Third step is go ahead to do the circuit analysis. Right? Same pattern, same pattern. So step 1, 2, and 3. In step 2, how to find these small signal AC circuit. Take care of the DC source, take care of the capacitors. Okay? And then you place the small signal model, once again available from page 7, okay? Right in the middle of the paper. And then extending the circuit terminal by terminal, terminal by terminal. Okay, remember this sequence. After having the circuit, you jump to the step 3, finding the gain, AC gain by circuit analysis. Here I'm providing an arsenal again. Now remember to use them. Okay, arsenal full of weapons. Okay. First of all, the output equation. Okay. Generally speaking, we are following certain Ohm's law. We can find output equals to something, remember? And then we are trying to establish the relation between the input AC source and the V pi. This is also same as in the MOSFET, right? MOSFET is trying to have a equation in terms of input source and VGS, remember? Over here is V pi, either VBE or VEB. And also, you might consider using voltage divider, and might consider using the V pi loop KVL, or even KCL at 3 different terminals. Okay, and also be aware that the voltage between VBE, voltage between the base and the emitter is the V pi. It might be useful. Yeah, VB minus VE equals to VBE, which is nothing but V pi. Okay, be careful. It might be useful. And the same rule here. Same rule here. Okay, you need to check or say count. You need to count how many unknowns and how many equations. Our number of equations should be 1 less than that of the unknowns. So you can't find any individual unknown. You know you can't, since the input is not given. Okay. You can only find the ratio between any 2 unknowns. And what we really care is the output over the input source. This is the AC gain. Same thing as in MOSFET again. All right. Any questions before we start to talk about the midterm 2? All right, if everything's fine, then let's go to the midterm 2 here.